Okay, this is a review for the third midterm. You already have received some mail from me that defines the individual components. It's the same format as the previous midterms, nominally 90 minutes, but between 8 and 12, so 4 hours. 3 questions, each question 110 points, total score 330, but graded or full score is 100% is 300 out of 330. So no different from the others. There are 3 questions. They're all basically equally weighted. The first is on Bernoulli Equation and also the energy equation derived from it, which you'll remember is just the Bernoulli equation with the pump terms and the head loss terms. The second is similitude and Buckingham pi. You'll notice that those have been on perhaps all of the exams, recent exams to date. And the final one is on Bernoulli again, but also with a part that is conservation of momentum. Oops. And it's conservation of linear momentum. So, and also pipe flow, I guess. On the website, it suggests that it includes topics of the energy equation, similitude and Buckingham pi, which are, I guess this is week 8, this is week 9, and this is week 10 and 11, but mainly 11 is pipe networks, and so that's not really on this. And so at least allows you a little bit of time to focus. It's perhaps useful to you to know the equations that you need, and I don't mind sharing those because I think it's not just what the equations are, but you need to know how to use it. So the first one is the energy equation in 2 different forms. You remember that it has to be written between upstream and downstream. So the upstream is always the first term that has the upstream stream tube, which is going down. The streamline velocities are these upstream and downstream locations. There may be a pump that is in this. And so, as it's written here, it's all written in terms of lengths or heads. And the downstream components are the pressures, pressure head, elevation head, velocity head, and any sum of losses. So these may be major or minor losses. The pump head is given as a length, but it's equal to the power of the pump divided by the unit weight and the volumetric flow rate. That's unit weight of the fluid and the volumetric flow rate, which I guess you could also write as being the same power of the pump, but being a mass flow rate and multiplied by G. It's the other way to write it. So this is the first form of the term in a physical energy equation in a physical sense. The other way to write it is in terms of enthalpies, and so in this particular case, the mass flow rate multiplied by the enthalpies always between out and in, and the kinetic term, velocities out and velocities in, and the potential energy term, which is the elevations out and the elevations in. And so again, this is equal to the net rate of heat energy in, net in, plus the net rate of work in also. So we've seen these equations before. So these are equivalent to each other. They're just written a different way, where this includes substantial changes in enthalpy that occur within the system. Buckingham pi, we've talked about, and it's really a recipe. And the major variables, I guess, that we deal with are Reynolds number, which is density, velocity, some length scale divided by viscosity, and it's equal to the inertial terms, inertial forces, I guess, divided by the viscous forces. And this is needed for kinematic similitude. There is the Euler number, which is pressure divided by density and velocity squared, which is the pressure force divided through by the inertial force. And this is needed for dynamic similitude. In other words, to represent equivalence between the forces on structures, equivalence in the flow field and what it looks like. You know, we talked about the flow around a cylinder changing from laminar to being turbulent. So if you look down the center line of this is laminar on the top and turbulent on the bottom. So these are physically different flow regimes. And so if you want to represent the behavior of a system, then it has to have kinematic similitude. The Reynolds numbers have to be the same. And if that's the case, then you can use that to represent the forces that are applied on the structure. And I guess the other precursor term is geometric similitude. So these are the three conditions. It has to be the same geometry. The model has to look like the prototype. Has to be kinematically similar. The flow fields have to be the same. And if that's matched, then the forces on the structures can be scaled between the model and the prototype. And finally, in terms of pipe flow, which is also the energy equation, but it includes this head loss term. And the head loss major. So these are the terms that fit, for instance, into this portion here. They're always positive. And so major losses are the frictional losses in a pipe, a friction factor, a length over diameter ratio, and a velocity squared over 2g. And the minor losses are those that occur in pipe bends, etc. And they're usually given by a factor, which is a non-dimensional number, multiplied by the velocity, the inertial term, v squared over 2g. And I guess it's important to remember that this velocity is not the velocity either downstream or upstream, but it's the velocity that occurs within the pipe system, the average velocity. So that's worthwhile knowing, I think. And I did say one of the solutions requires us to remember conservation of linear momentum, and we know for that the sum of the forces in any particular direction, well, it's a matrix, it's a vector rather, is equal to the mass flow rate multiplied by the velocity. This is a scalar, this is a vector, and if you're looking at doing it in just, say, the x direction, then this would actually be the sum of forces in the x direction are equal to the mass flow rates multiplied by the velocities in the x direction coming out of the system. And so that maybe is something that's previous to this little suite of material in the classes, but it's something that you will need for one of the questions. So have a look at that also. Only linear momentum, not rotational momentum. Okay, so those are the topical areas. And so I propose, as usual, just to go briefly through the material that we have talked about in class, just to remind ourselves exactly of what was in there. Transport theorem, well, we've used that to be able to derive these equations for conservation of mass, conservation of momentum, and conservation of energy. And so we used that in this particular case to do that for thermal and physical work. And there are two equations, we already defined them once. The first is they're the same equation. They're both essentially the same equation, but they're written one to include enthalpy as well as one which assumes that enthalpy is very small. They have to be written, as you remember, this is actually written backwards from what we often think about it. They're all one-dimensional equations, both one-dimensional equations, and they rely on velocities downstream or velocities out, and a velocity in, always positive. They allow us to have a pump input into the system, which would be either this or this. This is written a little bit backwards from the way we usually write this term first, but it's written this way. This is a term depending on how uniform the flow is across the boundary. It's always been equal to 1 in the cases we looked at, but it could be equal to different numbers, but not in your exam. Upstream pressure head, upstream elevation head, upstream velocity head, the pump power, which is positive for a pump, negative for a turbine, and head losses, which are always positive. If it's a pump in the system, then you can substitute this into here, and you get exactly that expression that we defined one page ago, which is that the pump head is equal to the power in watts, joules per second, divided by G times, I think we used uppercase M, but the same thing, same as this, mass flow rate. So mass flow rate times G is the same as the volumetric flow rate times unit weight of the fluid that's flowing. These two terms here are just equivalent to each other. You can show that for yourself if you so wish. So Bernoulli's equation with the head loss terms and the head pump terms. We'll talk a bit later about the head loss terms. And also Bernoulli's equation with the energy loss components, including enthalpy, again written between I guess this would be H1 and this would be H2 in this parlance. This would be H2 and this would be H1. So always one-dimensional flows. The velocities are always positive. Doesn't really matter because you square them, so even if they're negative, they come out to be positive. And including enthalpy, inertia, or kinetic energy, if you want to think of it that way, potential energy, the thermal energy into the system, or the rate of thermal energy into the system, and the rate of work energy into the system. So pump would be positive, and a turbine would be negative. So those are the basic expressions that you would need to solve the problems. I'm not sure that we need to deal with that. We've just seen this expression and talked about it in terms of the sign convention, which is just a net requirement. This is the mass flow rate. This is always positive because it's just written that way. And so it's not, it doesn't have directions or sign convention depending on whether it's in or out. We went through this example in class, I think, to be able to do it. You have a fluid going in at some enthalpy, coming out at some enthalpy. You know the velocity is in, and the calculation is to figure out exactly what the amount of work recovered or consumed in that is. So we know enthalpies, we know the velocities, it's horizontal, so we know the elevation changes, we know the mass flow rates, and so we just need to manipulate it to be able to write it in terms of the energy per unit mass flow rate. And so we went through that in class. So you've seen that. And it turns out to be this number. So that may have been the only example we did with that, the enthalpy equation. Most of the other ones were just with the straight Bernoulli-like equation. An example of pumping between a downstream location to an upstream location with a pump that has a certain pump characteristic in terms of its pump head varies between 200 feet at 0 cubic feet per second and 0 feet of head at 2. If you draw a line between those, the equation for that line is this. And so if you write the energy equation in the first way that we wrote it, the Bernoulli type way, and look at a streamline which runs through the system to things that we know, 0 velocities upstream and downstream, 0 pressures upstream and downstream. So these two terms disappear, these two terms disappear. There is a head loss within the system, which is this, which we know, and the elevation changes we also know. And so we can rearrange these equations, substituting this value in here, and we end up with, because the head loss is written as a loss term, KL V squared over 2G, the expression that we end up with has a head loss term in it. We don't know what, we know what the pump characteristic is, which is this. This is Bernoulli's equation. All that's left after we get rid of these other terms is the pump head, the head loss, and the elevation change between upstream and downstream. We can substitute the pump head into here, which is this equation here, specific to the flow rate, which is also Q is equal to velocity times area, the average velocity. And we also have an average velocity here in this, and we can solve, not so easily, but it's a quadratic for the flow rate that satisfies this equation ultimately. Probably a bit more complicated than an exam question. I don't think you'd be given one that you have to solve a quadratic, but the basic idea is the same. We talked about groundwater hydrology. I don't want to spend much time on that. You can read into that what you will, but it's a useful technique for the people who are in both petroleum engineering and environmental systems engineering. Basically says that if you can draw a flow net where the angles between the stream tubes and the equipotentials are all 90 degrees, and that it honors the boundary conditions of a specific magnitude of head, which is equal to pressure head, head which is equal to pressure head plus elevation head, and does not include the velocity head, because this is usually so negligible it doesn't matter. And so on this particular line here, if you looked at the pressure prism, then you'd find out that at this point there's a very large pressure that exists here. And as you go up to this point here, that pressure is completely replaced by the elevation of this. And so indeed the sum of pressure plus elevation, which is this, is equal to a constant value on this boundary. It's equal to a constant value on this boundary here, because it's in a lake, from the same idea that if you go down a swimming pool, the total potential head, H, is constant. As you go down deeper, the pressure increases, but the elevation goes down. And so if you can draw a flow net that honors the boundary conditions with an equipotential that's upstream, an equipotential that's downstream, and that the flow net that intersects those has a right angle between the flow lines going in this direction and the equipotentials perpendicular to them, you can very simply calculate the flow rate from this equation here. And that is the total flow rate per unit run into the page is equal to how many stream tubes you have. In this case, 1, 2, 3, 4. Divided by the number of drops. And going from this equipotential here, you go 1 drop, 2 drops, 3 drops, 4 drops, 5, 6, 7, 8, 9. And the difference in heads between upstream and downstream, in this case, it would be equal to this height here relative to this height here. And so you know this. And if you know this coefficient of hydraulic conductivity, which is meters per second, then immediately you get the flow rate through this. So it's an incredibly powerful technique. You might not need to study it too heavily for what's coming up, but it's an incredibly powerful technique. So this takes care of the frictional losses. This is basically the HL term, head loss term. So anyway, so I won't talk any more about that. Buckingham pi, we said, was part of it. Buckingham pi involves 3 non-dimensional parameters: Reynolds number, Euler number, and Froude number. Reynolds number is for kinematic similitude. The flow regimes look the same. Euler number is for dynamic similitude, to get the pressures that are applied on a structure, given that you satisfy the kinematic requirement. We need to satisfy geometric requirements. And the Froude number is for flows which have a free surface on them, which would give us a connection between gravity behaviors, like a bow wave around a ship. So in terms of the main part of similitude is being able to develop a number of non-dimensional parameters which are able to describe the system. And so there's a formalism to do that. It's called the Buckingham pi theorem, and it revolves around being able to figure out the minimum number, I guess the maximum number of dimensionless variables that describe the system, which are a minimum number. So you can calculate what those are in terms of describing your system by all the important variables. And so we did an example with pipe flow: velocity in the pipe, density of the fluid, viscosity of fluid in the flowing, the aperture or diameter of the pipe, and the pressure loss, which was the pressure change over the length of the pipe. And so here there are 5 variables. If you look at these, then this is length over time. This is mass per unit volume. And so time, mass, and length are all included. So there are 3 parameters, MLT, are all included. Total number of parameters here are 5. And so you'd expect to get 2 pi variables. You get pi 1 and pi 2. And those would be the variables that would completely describe your system. And so if you plot them, typically as maybe Reynolds number and Euler number, or 1 over Euler number, you'd have a single relationship that describes those. It doesn't need to be a straight line. It could be anything. And in fact, we know that in the Moody charts, for instance, it's a line that typically looks like this as we go from laminar to turbulent. And so the key then is to be able to figure out exactly how we are able to evaluate these non-dimensional variables. And so there's a formalism to it, and that is that we skip down through here. I'm just going to go through an example because you've seen this before. But if you look at pipe flow, for instance, where we have the diameter. We had B up above, but that's not right. The density, the viscosity of the fluid, and the velocity, and the pressure gradient along the length of the pipe that drives it. So again, 1, 2, 3, 4, 5 variables. If we write out those variables in terms of the units that describe them, we have mass, length, and time all represented. So we have 5 variables. We have all three groups representative, mass, length, and time. And therefore, we know that there are going to be 2 non-dimensional groups, pi1 and pi2, that describe that behavior. We select repeating variables. The important thing about selecting repeating variables is that the ones we select, and if you do have this in an exam, I guess you know you have this in an exam, you'll be given these repeating variables, merely because if you're not given them, you'll get slightly different non-dimensional parameters. You can always manipulate those into the other sets that you like, which would typically be Euler number and Reynolds number. But the repeating variables you choose should always represent every single one of the units. It should include length, should include time, and it should include mass. So these 3 would be appropriate because they include mass, length, and time in those 3. So if you take these as the repeating variables, then the other variables that are left would be the viscosity and the pressure gradient in this case. So these would be the non-repeating variables, or the dependent variables in this particular case. Then what we do is we want to be able to make the product of these repeating variables and each one of the dependent variables in turn match up with the units that have no units. And so the way we do that is we take each of these variables and we write out what the units are for each of these. We raise these each to a power, A, B, or C, which we don't know, which we'd like to find out. And we set those units equal to 0 units of mass, 0 units of length, and 0 units of time. And so long as we can satisfy this requirement for the values of these exponents, A, B, and C, then we have a solution that has no units in it. And so that's really what we're doing. And so since we have 3 variables, A, B, and C, we can write this equation 3 times in terms of mass, then length, then time. We can make sure that in each case that the variables, the exponents, sum to 0 on the right-hand side, and that's basically the solution. So the recipe is we take these. So we take, first of all, mass. This has mass to the power 1. This has mass to the power 0. This has mass to the power 0. And this has mass to the power C, not 1. 1 times C. And it has to equal 0. So that's the first equation. We do it for length. We take length to the power -2. We have length to the power A. We have length to the power B. And we have length to the power -3C. And that again is equal to 0. And then finally for the last one, for time, we have time to the -2. We have no time. We have time to the -1 times B, which is this, and equals 0. And so from this, we immediately know that C is equal to -1 from this. And we can calculate from this that B is equal to -2. So we have each of these. And if we take C and B and we substitute for each of these, then we also have this final one, which is A. If we take this and we make the first pi group, pi1 is equal to delta PL to the 1 times d to the power A times velocity to the power B times density to the power C. Then we have each of these values now. We can substitute for this, and we end up with this. And so this, since we know that delta PL times D is the same as dPdL times D, this is really a pressure on the top, this term here, and this is V squared over rho. So this is actually the same as an Euler number. And so we've done it once. So if you recall, we had 3 dependent variables, which are these ones that we used, repeating variables. We used the pressure as the first repeating variable, and we're left with one other repeating variable, which is the viscosity. So now what we're going to do is we are going to write them with the same 3 repeating variables, but with a new dependent variables. Before this was delta P L, so we just replace that. So it figures that since this behavior here, let me make it smaller, since these units here are exactly the same as the units here, then the whole left-hand part of this table is going to be the same. And so immediately, if we wanted to, you could take this table down here and you could just transplant it right here. Right, for these terms, for the diameter, for the velocity, and for the density, and this is the same as well. And so that is done. And the only things we have to add are the behavior for the viscosity. Viscosity, you could calculate viscosity if you don't know what it is. Its units of stress is equal to viscosity times a change in velocity with a change in length. If you rearrange that, I guess you'd have viscosity is equal to a stress multiplied by a length divided by a velocity. Don't need these d's. And so if you know what the units of stress are, you'd calculate that. Or if you didn't know what the units of stress are, you could write it as equal to force divided by an area. And that's also equal to mass times acceleration times an area. So if you know the units of mass, kilograms, if you know the units of acceleration, meters per second squared, and you know the units of area, which are length squared, then you can certainly calculate what stress is, and this would be length, and this would be length over time. So you could calculate exactly what it is, and it turns out that it's this. I never keep that in my mind, but I can also know how to calculate it. So now this is all to the power 1, and so so this is, if you like, this is to the power 1. So mass for the first equation is +1, and these terms exist from before. Length, which is the second equation, is -1, and the same components are in the second equation. And then time, this is -1 also, so this is here. And so again, you can do this. You can look at the first equation. This makes C is equal to -1. The third equation means that B is equal to -1. And if we know what B and C are, then we can substitute to figure out what A is, and that's this. And then we can write out this equation from before, which is equal to mu to the 1, d to the A, which is to the -1, velocity to the -1, and density to the -1. And so this is actually reciprocal Reynolds number. So this is actually 1 over Reynolds number. This is the top of Reynolds number, the inertial terms, and this is the viscous term on the bottom. So that's it. So that's it. So now you have Reynolds number, and so talk here about what you'd do if you had an extra term, which we didn't need. But if you have 2 terms, 2 pi terms, then it means that you would have a relationship which you could write in terms of those 2 pi terms. This might be Reynolds number, this might be Euler number, and you'd end up with some relationship which describes those behaviors. If you have some other factor, which for instance was roughness or relative roughness of the system, then you'd have a whole bunch of other curves in the same space, one curve for each value of relative roughness. And so this would be the pi3 term. So it allows you to be able to draw charts with a minimum number of experiments, which is basically the reason for doing that. So the utility of Buckingham pi theorem is that you end up with these dimensionless variables, and you can use them in experiments to be able to use similitude between the different systems. And so what you'd like is a model that satisfies these three requirements of geometric similitude, kinematic similitude, and dynamic similitude. And in that order, if you like. So geometric similitude means that the model looks like the prototype. So in other words, if it's a 1 in 10 scale model or a 1 in 100 scale model, that all the dimensions are shrunk down by that magnitude. It's not distorted in some way. In terms of kinematic similitude, again, to use the example that we talked about for flow around a cylinder, kinematic similitude means that the flow regime looks exactly the same in the model as it does in the prototype. So it means that the Reynolds number for the model is equal to the Reynolds number for the prototype, because it's the Reynolds number that indexes the flow regime. So if it's laminar, then the flow regime might look like this. If it's turbulent, then it might be with the boundary layer here and a whole bunch of separation and eddies falling down here. These are very different Reynolds numbers. So this would be a Reynolds number less than 2000, say, and this would be a Reynolds number greater than 2000. And it would change with different values of the Reynolds number. So the basic idea is for kinematic similitude, you want the Reynolds numbers to match. It means the flow regime in the model and in the prototype look identical. And if that's the case, then you'd expect that the forces that get applied on the model and on the prototype are not identical in size, but are scalable between typically the fact that the Euler number for the model is equal to the Euler number for the prototype. Which basically means that the pressure that's applied on the model is equal to the pressure that's applied in the prototype for whatever the velocities and the densities would be. So often the densities are the same because it's the same fluid, but not necessarily. You could be doing this, not in this particular case of the free surface, but you could be doing this with a gas, air, and you could be trying to scale it to a liquid. So, and this example basically makes that case. So I won't go through that. I'll just let you look at that on your own. Pipe flow is an extension, if you like, of the Bernoulli equation or the energy equation that we had before, which is really the Bernoulli equation. It has an upstream component. It has a downstream component. We always have to write it between the upstream and downstream. That's important. And it can have a pump in there, and there would always be some head losses in the system. And so we've talked before about what the pump head would be, so maybe we don't need to go through that. In terms of our terminology, this is W dot over gamma Q, unit weight of fluid times the mass flow rate. And the losses are either major losses or minor losses. Major losses are the small losses due to friction along the side of a pipe. They're small losses incrementally, but over a long length of pipe, they end up being, they sum up to something substantial. And so they're usually given in terms of the Moody chart numbers, which are this. A friction factor for Moody, the length of the pipe, the diameter of the pipe, and the average velocity in the pipe. Not the upstream velocity, not the downstream velocity, but an average velocity in the system. These are the upstream and the downstream velocities by contrast. So the major losses are small incremental losses, but they're summed over a long length of pipe. The minor losses are at the fittings and bends in the pipe, usually given by a coefficient of loss or loss coefficient, which is always non-dimensional, typically of the order, it can be larger than one, but typically less than one. The velocity in the fitting and gravity. Not sure. Yeah, I'm not sure you need those. If you look at pipe flow and the magnitudes of these friction coefficients, which go into this major loss, then for laminar flow, the friction coefficient is a function of Reynolds number and a coefficient. You'll remember for circular pipe flow, this was maybe 64. And they're defined in terms of the diameter of the Reynolds number is defined in terms of the diameter of the pipe, and which is also a function of the cross-sectional area times the perimeter, hydraulic diameter in this particular case, which reduces to being the actual diameter for a circular pipe. For turbulent flow, the friction factor is a function of the relative roughness. And so you'll remember that the friction factors for Reynolds number versus friction factor look like this. For a circular pipe, this is 64 divided by the Reynolds number. Reynolds number is density times average velocity times the characteristic length, which is always the hydraulic diameter, and divided by viscosity. This is 2000 when it's defined that way. This is laminar. This is turbulent. And these are for the transitional flow for different values of relative roughness, which is the pipe roughness, which is epsilon, divided by the overall diameter of the pipe, which is rough on both sides. So you guys know that. Yeah, okay. There's an extra term that sometimes creeps into this equation. It's not actually written here. It's not particularly important for us, so we didn't write it here or here. It's a number that's usually equal to 1 for all the things that we need to do. It might be smaller than 1 if we have a non-uniform flow. Not sure you need to worry too much about that. And there are a variety of different ways of solving pipe flow equations. We call them types 1, 2, and 3, and it depends on what you want to determine versus what you know. And so by far the easiest one is type 1, because you can solve usually in one step to calculate what the pressure drop is or what the head loss is in the system if you're given the flow rate, because this ultimately defines what the Reynolds number is, because it's a velocity, a diameter, a density, and a viscosity. So typically for fluid, you know both of these. If you know what the velocity is, and if you know the diameter of the pipe, then you certainly know on the Moody chart diagram exactly where you are, right? If you know what the Reynolds number from this, because you know both this and this, then you know exactly where you are. You know what the friction factor is. And if you know what the friction factor is, you can calculate what the pressure drop is, because you know exactly what this is. It gets a bit more challenging if you want to calculate a flow rate, if you have a pressure drop that's applied or a head loss that's applied in the pipe, and you know the diameter of the pipe. And it's also challenging if you want to be able to calculate the type 3 problem, where you want to size the pipe to be able to carry a certain flow rate, because here you don't necessarily know what the friction factor is, then you have to iterate towards it. This is a summary of the Bernoulli equation with the head loss. I guess it's the energy equation. We know what the pump heads are. We've said that a number of times already today. We know what the head loss terms are in terms of either major losses or minor losses. Always have to write it from upstream to downstream. the velocities are always positive. They're streamlined velocities. Yeah, we spent some time talking about this chart. So friction factor, which is analogous to an Euler number or an inverse Euler number. Reynolds number, which is defined in terms of the pipe diameter or the hydraulic radius. Sorry, hydraulic diameter. Typically around this number of 1,000 or 2,000 we've often chosen. This is 2,000 here. Is this change from laminar flow to transitional flow? If the roughness of the pipe is 0, then that's the definition of smooth, which is this lower bounding behavior here. And if the pipe has a variety of different roughnesses, which are these values getting increasingly rougher as you go in this direction, then you can calculate exactly what this is. And so the important thing, or the useful thing, is that if it's fully turbulent flow, you only have a single friction factor to deal with, right? Because at a given high Reynolds number, for a given roughness of the pipe, you have a single number, and this doesn't change. So it makes the solution much easier. If you're in this laminar regime, when you go up here, the friction factor is always a function of the Reynolds number. And so a different regime, it changes as Reynolds number. And so if you're trying to solve it as a function of Reynolds number, you need to keep this in the equation. If it's in the case that it's for turbulent flow, then the friction factor is always the same. And so sometimes, I think 1 or 2 occasions, we've given you a Moody chart. Most of the time, we'll give you a friction factor and allow you to do the calculation. And that's it. And so even though, strictly speaking, in this unit, exam 3 unit, week 11 is included, which is pipe networks, then there isn't one in this particular case. So that's it. So to reiterate, maybe it's worthwhile going back to what we talked about before, just to say what the 3 equations are. Bernoulli energy equation, they're the same equation. Essentially, the energy equation has head loss and pump heads in it. That's the only thing that makes it different from Bernoulli. Similitude is a recipe of being able to define what the parameters are, the pi groups are, that give you similitude between a model and a prototype. They usually work out to be in Reynolds numbers or Euler numbers typically. They could be in terms of other parameters for different systems, but those are typically the ones that are important. And our interest is in being able to have them geometrically similar, kinematically similar, and dynamically similar to be able to solve a problem. And the third question is Bernoulli, which is really the same as the energy equation, with or without these, but also with conservation of linear momentum. And conservation of linear momentum is that the sum of the forces is equal to the mass flow rate times velocities. And you can resolve that in whatever directions you see fit with an appropriate control volume. And that's written down here. So that is, yeah, that's it. So I think it's, again, you did well on the second exam. The average came up by 25%, and that's great. And so hopefully this will be the same deal. Okay? Thanks very much. Good luck.